Okay, so last time we did the harmonic analysis and we applied Fourier series that is that can be used to represent any periodic function or motion. So the unknowns in the series are the coefficients that we determine. Then the series is completely representing the given periodic function. So the problem arises in periodic functions in general are defined over intervals, and this can be smoothed out by using the sines and cosine terms. Okay, so that is one of the main reason of using the Fourier series. Okay, so the properties, when you use the properties of sine and cosine, then you can find the coefficients an and bn. Those are the Fourier series coefficients. And then for this, if x is even, then that bn, all b's will be 0. bn, b1, b2 will be 0. And if x is odd, then an will be 0, but not necessarily that a0 is 0, because a0 is the average. Okay, so here we have an example that we have. This is called sawtooth periodic function. So we can apply the Fourier series on this one to find the coefficients of the series, and that can be represented by the series. Okay, so to find a0 is first of all, we can find all the coefficients. Okay, so I can do this on one side. Okay, we have the example of sawtooth periodic function, which is given and so on. So we have the amplitude is A, and the time for one cycle is tau, and here is x as function of t, and this is time. So you can, for one period from 0 to tau, you can give that x equal to a over tau, which is the equation of the straight line, times t, and this is valid for t greater than or equal to 0, less than or equal to tau. Now this function is odd or even. Okay, you can check that by substituting for negative t, and if it gives you negative x, then it is odd. Okay, so this is odd. Which means that an will equal to 0, but we have to check for a0. Huh? If an is 0, which is a1, a2, a0 is defined as 2 over tau, integration from 0 to tau of x of t dt. Okay, you can go back to the equation for an, which is 2 over tau, integration from 0 to tau of x of cosine 0 is 1. Okay, so integration of, we substitute for x is a over tau times t dt from 0 to tau. So we take a over tau outside the integration. This becomes 2a over tau squared. and the integration of t dt from 0 to tau, which is t squared over 2. 2a over tau squared. This is t squared over 2, and the limit from 0 to tau. So this becomes a. Okay, this becomes a. Okay, in the series, we have, if we go back to the series, it's a0. In the series, it's a0 over 2. Okay, a0 over 2. So it's going to be, the first term is a, this capital A over 2. To find Bn, so we find all A's now. A0 is A, and all other A's are 0. Then we need to find Bn. Okay, Bn is 2 over tau, integration from 0 to tau of x of t sine omega nt. Okay, so Bn equal to 2 over tau, integration from 0 to tau of x of t, which is equal to a over tau times t, multiplied by sine omega n t dt. So we can take the constants of outside. So this becomes 2a over tau square integration of t sine omega nt dt from 0 to tau, and we can do the integration by parts. Okay, so you can just use the table. Here it is t, here is sine omega nt, differentiation of t is 1, then 0, integration of sine is minus cosine omega nt divided by omega n. Okay, integration one more, it's minus sine omega nt divided by omega n squared, and then you multiply this term by this term and this term by this term, and then you use plus, multiply by plus, multiply by minus. Okay, so Bn becomes equal to 2a over tau squared, and this becomes minus t cosine omega nt divided by omega n, plus sine omega nt divided by omega n squared from 0 to tau.
اوميجا سكوير ان سكوير. اقول مو اوميجا سكوير ان سكوير.
ما فاهم منك. اوميجا ان سكوير عندي.
ولا اوميجا مو بعد سكوير.
لا اوميجا سكوير.
والان بعد.
هي اوميجا ان يعني اوميجا 1 سكوير او اوميجا 2 سكوير او اوميجا 3 سكوير كذي.
اوكي.
اوكي اوميجا ان is the subscript يعني اوميجا 1 اوميجا 2 سكوير from 0 to tau.
Okay.
Okay, so this becomes 2a over tau squared, and when you put t equal to tau, so this is minus tau, and cosine omega n, we know that it is 2 pi over tau, يعني 2 pi n over tau. Okay, definition of omega is 2 pi over tau, and since this is omega n, n is integer. You know, we mentioned this last lecture that n is integer. So if n equal to 1, then this is 2 pi over tau. If n equal to 2, this will be 4 pi over tau. If n equal to 3, this will be 6 pi over tau, and so on. Okay, so I'm going to use that definition of omega n here. So it is going to be 2 pi n over tau times tau, which is inside the cosine, divided by omega n, plus sine 2 pi n divided by tau multiplied by tau divided by omega n squared, minus when t equal to 0, so this becomes 0. Because t is 0 multiplied by cosine, then it is 0, and sine 0 is also 0. Okay, now when simplifying, cancel tau and tau, and cancel tau with tau here. Then 2 pi n is integer. Okay, so this becomes, for the sine term, sine 2 pi is 0, sine 3 pi is also 0, sine 4 pi is also 0. Okay, there is no 3 pi, sorry, there is always multiply by 2, so it is 2 pi, 4 pi, 6 pi, and sine 6 pi or all the multiples of 2 pi is 0. So this becomes equal to 0, this term. And cosine 2 pi, if n equal to 1, it is 1. And cosine, when n equal to 2, it is 4 pi. Again, it is 1. So this becomes cosine 2 pi n is always equal to 1. Okay, and omega n, I'm going to use the definition of omega n. This is 2a over tau squared. Okay, so let me just make this equal to 0, and the cosine is equal to 1. So this becomes here minus tau over 2 pi, omega n is 2 pi n, okay, divided by tau. So this becomes tau squared. Okay, so as you can see, tau squared cancel with tau squared, and 2 cancel with 2, and this becomes minus a over pi n. Okay, so that is the final value for Bn. The series can be now written as x of t equal to a0 over 2 plus summation of n equal 1 to infinity of Bn sine omega n t, right? Because an is 0, except a0 is not 0. And now we can substitute for the coefficient. So we have a0 is a divided by 2 minus, as you can see, there is minus here, minus summation of n equal 1 to infinity, and Bn is a, we can take a outside. You can take a and pi outside as common factor, summation of n equal 1 to infinity of 1 over n sine omega n t. So you can expand this as a over 2. When n equal to 1, this is a over pi sine omega 1t minus a over 2 pi sine omega 2t minus a over 3 pi sine omega 3t, and so on. If you look at the coefficients, starting from term number 2, Okay, so this is first term. This is second term in the series. This is third term. And this is fourth term, and so on. The first term is giving the average of the, if you just take the first term, then you will get only the average. The coefficients of the terms, except the first term, the coefficients of the terms are what they have 1 over n. Okay, I will remove this bracket. It is 1 over n. It means it is decaying. The coefficients are decreasing until when n equal to infinity, 1 over n is 0. So it means if n is high, the contribution of that term is neglected. So this series converges. If we go back to the solution we have here, this is the A0 term over 2. Okay, this is the first term, which is shown here by dashed line. So one term approximation, the series has infinite number of terms. If you only take the first term, this will give you a straight line, which is the average. If you take the first term and the second term, we have two term approximation, then you have an oscillations about the actual function. Okay, those are the this big one. This is with two terms approximation. And if you go up to 3 terms approximation, okay, this one, you will have this function. Okay, so as you increase the number of terms, you will get the approximated function going along the actual function. Okay, so as you can see, with the 3 terms approximation, you have almost moving along, the approximated function is moving along the actual function. So if you increase with more terms, you will have an approximated function that is giving you exactly the actual function. So this is with the 3 terms, and you can see it is following the actual function. This is the Fourier series, and due to the truncation, it means you will only take a few number of terms. You will get something called Gibbs phenomenon. Okay, as you can see here, with n equal to up to 8. So it is smooth. When you increase n, you get a smoother curve along the actual function, but except at the transition. The error is getting bigger with increasing number of terms. So it is accepted all over, except at the transition you have the Gibbs phenomenon. And the reason is of getting this Gibbs phenomenon is the truncation we do in the series. We cannot go to infinity. So we will have this problem at the transition. So some of the periodic function will exhibit Gibbs phenomena when you use a Fourier series. Okay, so it is accepted everywhere with almost zero error, except at the transition, which is the end of the period of the cycle. Okay, that interval. Usually in practice, if you rarely maybe have this kind of periodic function. But in practice for vibration, the measurements is for machines. For example, if you measure vibration of machines, machines are excited mainly by harmonic forces. So it is not same as this periodic function. Harmonic function, then you will get exactly the actual function because it is already harmonic. So if you use Fourier series to approximate a periodic function that is made of harmonic function, then you are getting exactly the function, the actual function. But this is not harmonic. So Fourier series is excellent for approximating harmonic functions. That is, it can be measured, measured vibration or measured motion resulting from harmonic excitation. Okay, but in general, it can be used for any periodic function, and you will have this Gibbs phenomenon. One of the important things of the Fourier series is plotting the coefficients versus frequencies. Okay, so let me just give you an idea. This is called frequency spectra. Okay, so this is frequency spectrum. Which is a line plot of the coefficients versus frequency. Here, AN is 0, and A0 is not multiplied by sine omega t. So it will, I will not put that one. I will put only Bn. Okay, so this is Bn versus frequency. And the frequencies are omega 1 plus our points, omega 2, omega 3, omega 4, and so on. Omega 1, B1 is 1 over, is A over pi N, and N is 1. Okay, take the absolute value. Okay, so here it is, absolute of Bn. So it is A over pi. Let's say A over pi is here. Then we can show this by just a line. With this value is A over pi. And when the second term, or B2, is A over pi over 2, which means half of this. And when it is 3, it means it is somewhere here. A over 6 pi, over 3 pi. And A over 4 pi. So it means that and so on, this will decay as 1 over x. Okay, so say this is converging series. So that a few number of terms will be enough to represent the actual function, except that there is a problem at the transition. You get an error. That is the Gibbs phenomena. Okay, this is for non-harmonic periodic function. But in practice, usually we have excitation in machines due to harmonic forces, like the imbalance is one of the excitations. So it will give you that will be very close to the actual. And of course, in the actual one will have some noise. Okay, but okay, it's going to give you a good approximation of the actual wave measured or the motion measured. Okay, this is very important figure. It's called frequency spectrum, and that can be used to identify errors or damages in the in machines. This is called use in the monitoring of machines or vibration measuring, vibration monitoring of machines. Okay, any questions? Okay, vibration terminology, peak value, this is the maximum value as we saw in in X, that is A is the amplitude or peak, and for the velocity omega A was the peak value, and for acceleration omega square A was the peak value. This is a peak. The peak value is used in many applications, including measuring the vibration of a sleeve bearing. Okay, sleeve bearing, there is a shaft inside a sleeve, and this sleeve is fixed. Okay, and the shaft is rotating with this omega, and inside there is oil to prevent the to minimize the friction between the shaft and the sleeve. So the shaft is usually supported between two sleeve bearings, and it should rotate about the center of gravity. Let's say here it is the center of the shaft. But of course, due to the centrifugal forces and the center of gravity might be shifted even with a small amount, this will give you imbalance forces. So the shaft will not rotate about this point or the axis through this point. It will have a circle. Okay, it's going to move. Instead of rotating about a line going through this point, it's going to move about a circle. Then an important measurement is to keep clearance always under within the accepted limit. So here is a clearance. This is a clearance to be always kept as a safe value. Okay, this gap, the gap to be always watched. So that when the important thing is to have the peak value does not reaches to the safe clearance gap. So always measuring the peak value here. They use a sensor. They make a hole in the sleeve, and then they put a sensor. It's called a proximity probe that measures the gap between the shaft and the sleeve. So if the peak is very close to the gap, then there is a problem. So in this case, you need to measure the peak value. Okay, so the vibration might be something like this. You want to see how much is this point or the peak value. Okay, the maximum value. Average value is also used. It indicates steady or static value. So we have sine wave. The average value is 0. This is sine omega t. If you have sine omega t, then the average is 0, which is indicating that there is no vibration. If you take the average, and this is the equation for the average, x bar equal to the limit of 1 over t from integration from 0 to t of x of t dt as t goes to infinity. So you take, it means you take all the readings and then you take the average of the readings. If it is a sine wave, then the average is 0, which means that if you take this as a measurement of vibration, that means there is no vibration. So in order to overcome this, you can rectify the sine wave as, and then you take the average. Okay, the rectifier, it means you make the minus plus. So this is the absolute of sine wave. Then the average here is not 0. And you can get the average equal to 0.637a of the rectified. This is the rectified. Another way is take the mean square value. You take the square. So you have sine squared. This is sine square omega t. Again, the average, if it is a sine wave, it is not 0. So you take the average of the x squared. And this becomes equal to 1 over 2 a squared. This is the average of sine squared. The common average used is the root mean square value, RMS. So after you take the average of x squared, then you take the square root. Okay, so the RMS is equal to, for sine wave, square root of a square over 2, which is equal to a over square root of 2 equal to 0.707a. So that is the RMS value of the average, which is RMS is used for measuring the x, or the velocity x dot, or even the acceleration. Also used in by electrical engineers, RMS of the voltage or RMS of the current. Okay, so you rarely will find that devices give you the actual average. They give you the RMS value. So they measure vibration by RMS to avoid having a sine wave that gives you an average equal to 0, which indicates there is no vibration. Okay, so this is an average value, but RMS, average. Okay, it is called RMS, which is root mean square value. Okay, another decibel is also used as a unit to give indication of vibration. It is defined as 10 log base 10 of power 1 divided by power 2. We have in mechanical engineering that power is related to quantity squared, like x squared. So if you replace the definition of power by x1 square and x2 square, then you can use the properties of logarithm. This becomes 20 log base 10 of x1 over x2. X1 is measured value. And x2 is the reference value. Okay, and decibel is used in noise for sound, as well as in the vibration of bearings. You can, they are assessed by decibel, or the vibration is quantified by decibel in bearings, or high speed, vibration. Okay, now we can, this is the end of chapter 1. I will print here a tutorial. Just a few seconds. This is lecture 3 and 4. Okay, in tutorial 1, I put a summary of some selected problem that can summarize the chapter. In chapter 1, we talked about definition of vibration and then the types of or harmonic motion in a specific, and then the Fourier series. Okay, those are the main things that we did with the terminology at the end. Here are questions related to harmonic motion and Fourier series. Question 1, we have harmonic motion has an amplitude of 0.2 centimeter and a period of 0.15 second. Determine the maximum velocity and acceleration. So the maximum means the peak. Harmonic motion, it means that x equal to a sine omega t. And a here is equal to 0.2 centimeter. Okay, so this is a, the amplitude, and the period of oscillation, this is tau. A maximum velocity is V max equal to A times omega. This is the maximum velocity. Okay, and omega is equal to 2 pi over tau. So you can get the answers. Here we have the answers are given in centimeter per second. So A is 0.2 multiplied by 2 pi divided by 0.15. Okay, the maximum acceleration is equal to A omega squared. So you can do the same thing. Question 2, an accelerometer indicates that a structure is vibrating harmonically at 82 CPS with a maximum acceleration of 50 g. Determine the amplitude of vibration. 82 CPS means hertz, cycles per second. This is 82 hertz, which is F. Okay, with maximum acceleration, that is A maximum equal to 50 times 9.81 times g. Okay, usually in the acceleration is compared with the gravitational acceleration. So it is 50 g, it means 50 multiplied by g, or 50 times 9.81, which will give us acceleration in meter per second squared. Okay, determine the amplitude of vibration. So we can use the definition of the maximum acceleration, which is equal to A omega squared, and find from here A, right, which is equal to A maximum over omega squared. Omega is equal to 2 pi F. Okay, this is omega is the circular frequency, F is the cycles per second frequency. And they are related by this equation, omega equal to 2 pi F. Question number 3, a harmonic motion has a frequency of 10 cycles per second, and its maximum velocity is 4.57 meter per second. Determine its amplitude, its period, and its maximum acceleration. Okay, so we have the maximum velocity is given, and we can use the definition of the maximum acceleration, which is a omega, and find a, which is the amplitude. And 10 cycles per second, it means this is the frequency, f, and the period, it means 1 over f. Tau is 1 over f, and you can find the period. And the maximum acceleration is after you find a, okay, so it is a times omega squared. That will give us the maximum acceleration. Question 4, the maximum amplitude and maximum acceleration of the foundation of a centrifugal pump were found to be 0.25 millimeter and 0.4 G respectively. Find the operating speed of the pump. Okay, the centrifugal pump, it means you have a rotating part. Okay, you have the impeller is rotating with angular speed omega, and also this is causing vibration to the foundation. Okay, this is the foundation of the centrifugal pump. Then the vibration will have a frequency. Omega is the speed of the impeller or the shaft of the centrifugal pump, and also the frequency of excitation. So omega is speed, and as well as considered to be the frequency of excitation, as we saw this in the Scott-Check mechanism. The crank is rotating at angular speed omega, and the rod is reciprocating with a frequency equal to omega as well. The same units, radian per second, or even in hertz. Okay, you can put that in hertz, like if. So we have amplitude, the peak amplitude is given 0.25 millimeter, which is A, and 0.4 G is A maximum. So use definition of Amex equal to A omega squared, and you can find omega from here because this is 0.4 times 9.81 equal to 0.25 multiplied by 10 to the power minus 3. Okay, we have to use the same units, right? Consistent unit. 0.4 G is meter per second squared, and A has to be converted to meter. This multiplied by omega squared, you can find omega. Omega is in radian per second. Answer is given in hertz. So you need to find F equal to 2 pi equal to omega over 2 pi. And this should equal to in hertz. Question number 5, find the Fourier series expansion for the rectangular wave shown below. It means you find the coefficients A0, AN and BN. Find the root mean square value, RMS, of the average, and plot the spectrum, the frequency spectrum. So the wave is repeating itself. This is given by omega t. So this is the first, this is one period from here to here is one period. Okay, so you can find, you just follow what we did in the example. Here, instead of integrating from 0 to tau of dt, you will just break it down into from 0 to tau over 2 dt plus integration from tau over 2 to tau dt. And the reason is x is defined, it says x equal to 1 for t greater than or equal to 0, less than or equal to tau over 2, and x equal to minus 1 for t greater than tau over 2, less than or equal to tau. So it is given as piecewise continuous over one period. Okay, in the example about sawtooth periodic function, it was continuous within the period tau. From 0 to tau, it is given by one equation. Here it is given by two values, 1 and -1. So whatever integration you have to break it into two integrals. Okay, so you can find the coefficients. Also make use of the even or odd functions. A0 is 0, as you can see, because here we have a plus and minus within one period. So average is 0, which is A0 is 0. And if you use t here and you find at minus t, you can see they are equal but opposite in value, in sign. So this is even, this is odd function. Okay, for odd, we have an is 0. So without doing the integration, you just mention that this is odd function, and the average is 0. Then all a's are 0, a0 up to infinity. All an are 0, and then you need to find bn by doing the integration. Okay, question number 6 is if you compare. This is called crank piston mechanism, which consists of of a connecting rod with length r. Okay, we have, crank with r, and we have connecting rod with length l, and then we have the piston, which is moving in rectilinear motion. This is the crank piston mechanism, consists of three elements, right? The rotating crank, the connecting rod, and the piston. So you are converting rotation to reciprocating motion, or vice versa, reciprocating motion into rotation. This is the if the crank is at 0 angle, which is along this line, the connecting rod is along also the center line, then this will be fully extended. The piston will reach the maximum lift end. So you can make this as a reference point. Okay, this is the reference here for the origin, from where you measure the position of the piston. So if theta equal to 0, then S is also 0. And you can find the equation for S. Now theta is at the end can be just keep it as it is, but it is related to the angular speed, omega. Okay, so you can keep the terms in terms of theta, but you know that theta is equal to omega t. So we relate this to time. The purpose of adding this question here in the tutorial is to tell you that the Skalchak mechanism gives the reciprocating motion of the rod as a sine wave, which is a simple harmonic motion with one term, that is x equal to a sine omega t. But with the slider, with the crank piston mechanism, the motion of the piston is complex harmonic. Okay, it will give you an infinite number of harmonic frequencies, which will not be a simple harmonic motion as with one term, a sine omega t. It's going to be very complex. Okay, but the mathematical part of this is is lengthy, you need to use binomial theorem in order to make an approximation to answer the question. So what is saying that if R over L is 1 over 3, what is the ratio of the second harmonic compared to the first harmonic? It means you will write S as S0 or A0, or I'm going to just use C0 plus C1 sine theta t plus C2 sine 2 theta t, which is 2 omega t, plus C3 sine 3 theta t, and so on. Okay, this is the constant part. It might be 0. And then C1 is the first harmonic term. It's saying here the ratio of second harmonic compared to the first harmonic. So this is the first, and this is the second, and this is the third harmonic term. The questions when R over L equal to 1 over 3 wants to know the C2 over C1. What is the ratio of C2 over C1? The equation for S is not going to be straightforward given as shown here. You have to use binomial theorem. Okay, and this is the mechanism that is used in the car engines. Okay, and causes noise. So unless that you have R over L is small, then you can see by the answer. Okay, the ratio is 1 over 12. Okay, so if this is if C1 is it 12, then C2 is 1, which is very much smaller than C1, and C3 will be even smaller. So although this mechanism produces complex harmonic, but choosing a proper value of R over L, you can ignore higher order harmonic terms. So this can be approximated as S equal to C0 plus C1 sine theta t. Okay, and you can ignore the rest. Okay, so you can skip question number 6. This will be very lengthy and requires to use binomial theorem. And I don't want to take you back to the calculus. Okay, you can skip question number 6. So try to solve question 1 to 5 completely. And in case you have questions, you can ask me next lecture. Okay. Any questions so far?
دكتور
Yeah.
السؤال الرابع شلون عرفت ان الاوبريتنج سبيد يبغيها بالهرتز؟
انا عرفتها من الاجابه بس يعني ممكن مقبول انك you can answer by giving the frequency in radian per second or in hertz. Anyone is okay, is accepted, unless the question is asking specifically about certain unit. فهني ما حدد بس أنا I saw this from the answer. Okay, so we'll see you inshallah next time.